Yeah, as our next speaker, we have Jorge Vargas from UNEC in Argentina, who's going to speak to us about restriction of square integrable representations. So thank you very much.
Oh, thank you for accepting my talk. And really what I wanted is to visit Brasilia and recall old times I lived there. But pandemia does not allow us to do that. What I want to talk is maybe restriction of square interval representation. I will not able to talk in 20 minutes about that, but some results about restriction of representation that might interest you geometers. Actually, I feel somewhat, except for the last talk, the previous talk, I feel like a frog in a wrong pond because all of talks have been very nice and in geometry. So we start with a couple of groups, H inside G, H close in G, and mostly we will be compact, but the main results that refers to the talk are for G and H non-compact. But as I said, we won't have time for that. For example, if you want to think of a pair of examples, SUN inside SUN or SU2N, the symplectic group inside the SU2N. And now we take a unitary irreducible representation of the big group G. And we collect all the H irreducible subspaces. If G is compact, there are a lot. But if G is not compact, there might happen that there is none. There is none except the trivial one. So we collect all the closed invariant subspace under the H axiom. We add them up, that we get an algebraic sum, and we take the closure. And if the representation is good enough, we get the whole B. And in this case, we call the representation H discretely decomposable. So in the case of G is compact, this theorem is true always. If G is compact, H will be compact, H is then compact, and any representation is H discretely decomposable. An example of non-compact discrete decomposable is, for those you know, take the Berman space defined by lambda on the unit ball in Cn. That's an irreducible representation of UN1 unitary, and the axiom is here. And there, we take H, the matrix with 1 and the diagonal lambda, and then a UN minus 1 matrix. And there, here in this case, you find a lot of closed invariant subspaces are these. Just take Z1 to some power and multiply by any holomorphic function that's not too bad in growth, and you get the subspace NK. And since any holomorphic function can be written this way, then this give you the discretely decomposable. So an objective that I want to talk now, and something more complete, is take a unitary reducible representation of G, assume that representation restricted to H is discretely decomposable. That's the case always if G is compact. And these are the H. And assume that, you always can assume that, well, a lot of time, that the V can be modeled in a space of functions, sections of a vector bundle over G, and the closed invariance H irreducible subspace also can be modulated on as spaces, subspaces of sections of vector bundles over H. So the V tilde is a model of B in functions in G, and the N tilde I is a function space on H that models the representation in Ni. And what we want to, now that we have a space of functions, usually they are square integral functions, or holomorphic functions, or real analytic functions, L2 functions that are real analytic, functions that come from kernels of elliptic operators, either in B tilde or the V tilde, N tilde I, are L2 solutions of the elliptic operators. So one wants to know the structure of the intertwining maps. This means that from B tilde to N tilde I, we will have continuous intertwining maps, H maps. Also, we have inclusions, T from N tilde into B. And we will have, since this is discretely decomposable, we have isotypic components. This is just collect all the reducible pieces equivalents to Ni. Closure that, and you get an orthogonal projector. And the question is, are they integral operators, differential operators, or maybe integral differential operators? If you look up at the books of Thelomenko, classical books on branching law, they always showed that some of these maps are differential operators, but they never write the theorem. So I wrote the theorem for compact groups. Actually, the theorems we prove with Ørsted are for non-compact groups, but I will not get into that. So the setting is a compact group, a unitary irreducible representation, that will be finite dimensional now. We fix a model V tilde and sections of a vector bundle over G for V tilde, and the same for the Ni's. And for example, let's say the preheating example, a heating example. G equal to H. G equal to H, and we take a finite dimensional representation of a subgroup K of G. We consider the homogeneous vector bundle over G mod K, and the L2 sections of these homogeneous vector funds. We know that because of Robinho reciprocity, this L2 decomposes as by the left regular representation, a sum of isotypic components, and these are finite dimensional. These isotypic components are finite dimensional. And as a G module, there is a finite sum of representation, and this number is called the multiplicity. Now, think of each irreducible representation of G realizes sections over some smooth sections over some vector bundle. Then we want to compute the intertwinings from the big space into the BG nu. This intertwining might be zero if BG nu does not contribute. If the isotypic component related to BG nu is zero, then the only chance is S to be zero. And we want to understand the orthogonal projector onto the isotypic component. And the answer in this case are very nice. Any intertwining from the big representation into the small, into this irreducible representation, realized as a space of sections of some bundle, is always an integral operator, and is always a differential operator, restriction of the differential operator. Now I'll explain you a little better what is this. And the orthogonal projector also is always an integral operator. However, in general, it won't be a finite order differential operator, but it is an infinite order differential operator. Now I'll explain all of this. What we got is the similar statements for in the infinite and the non-compact setting, but with some hypotheses. You need restrictions. So these intertwinings are called symmetry breaking, this S. These are integral operators and differential operators. Now I explain what it means that. We think BG nu as a space of section in some bundle. Here it is. Smooth sections in L2 bundle. We have the hard measure on G. Either W or Z has G invariance inner products by the subgroups. In this case is K. Here I think it's H I wrote. And now take an F and G, Z and Z. Then this F of Z, and F of Z is a function on here and in this space, VG nu, that's inside these smooth sections of this bundle. So we can evaluate the next, make the inner product in Z, and we get the numbers. So in this F and the X and the Z give rise to a linear function on L2 of G cross tau W. But it's continuous because the S is continuous and this V is G nu is a finite dimensional vector space. So all linear functions are continuous. Composition of continuous. This is continuous. This is a Hilbert space. By Riesz theorem, you get a function that represents this linear function. Well, we call it this fancy way so that we get the kernel. This way we get the kernel. So the ingredients to get the kernel is that the target space is a space of smooth functions. And point evaluation in this target space is continuous. From this, we get that the S and some work is represented by a nice kernel. Actually, one can show this kernel is smooth and so on. And how do you catch the differential operator? With the kernel, if you freeze the second variable at the identity, actually the function that results in the first variable belongs to the isotypic component. And the isotypic component, since it's a finite dimensional J module, is a finally generated UG module under the left axiom of UG. Therefore, you can choose nice generators, for example, the lowest weight vectors, but there are much better generators. And you get these functions represented as a finite sum of derivatives of this. Well, some work shows that you can prove that S of f of x is a sum of Vk of x, LdK. So it's a differential operator. So for the orthogonal projector is the same joke. So you do the PG change S. However, there is a big difference. The orthogonal projector in general cannot be represented by finite order differential operator like the projector into the irreducible component. That's a very somewhat striking result. The generalization is the same story with G and H. You take an irreducible representation of G in B inside smooth sections, and pH representation of H realized as smooth sections. And then you have three families of operators. The map the H intertwinings from B into the irreducible BH, the immersions of the BH in B, and the orthogonal projector. And that using similar techniques, you can prove that the three are integral operators. The three types of operators can be represented by integral kernels. It's the same trick. S and T are S and P nu. In this case, V is finite dimensional. So the orthogonal projector is again a differential operator. Whereas here in the infinite dimension case, the orthogonal projector is not necessarily differential operator. And the inclusion here sometimes is differential operator, sometimes not. We don't have a criteria for this. That seems nobody knows this when the inclusions are differential operators. It all depends how H, the subgroup, sits in G, and if you can find a complement, some sort of complementary subgroup H naught to H in G. In the examples, at least, shows that that works some way. This works some way. If G can be written as H times H naught, some subgroup H naught. So in the general case, let me tell you some objectives that we had, and we solved the problem, some problems. This problem comes from very different sources, number theory, physics, and so on. Find families, now H and G are general, not necessarily compact. Families of unitary representation of the big group, irreducible, so that each of them, when you restrict it to H, are H discretely decomposable. This is when the pair GH is semi-simple and G is a semi-simple group, this more or less has been achieved by Toshiyuki Kobayashi in Japan and his students. I also contributed in the case the family as discrete series, but they have much better results. Among these H discretely decomposable families, to find those that are H admissible. And this means the multiplicity of each irreducible factor is finite. So we need criterions for this. We need criteria to detect when a given representation is discretely decomposable or H admissible. Well, let me now, I will talk in abstract. If you take G semi-simple and take an elliptic operator, or take a maximal compact subgroup K and take an elliptic operator, then you can consider the space of L2 sections of this elliptic operator in some vector bundle over G, so over the symmetric space attached to G. These representations are called square integrals. And the irreducible factors, if there are, when restricted to H, belongs to the same family. Belongs to the family of square integral representations of H. So you are in this picture, forget the word compact. And the same questions again. And the answer is that these three are always integral operators. Now we can show that the S from the big representation to the small, if there is one S that's represented by a differential operator, then the representation is discretely decomposable over H. And conversely, we can show that V restricted to H is discretely decomposable if and only if the intertwinings from B into H square integral representations are always represented by differential operators. And moreover, we get admissibility. Well, I had all of this written, but I think I better stop here. All of you are tired from this wonderful Congress and very nice talks. I listened to some of them. I really enjoy. So I would like to thank the organizer for such a marvelous job. And once again, thank you very much for your time.
Oh, thank you very much for the talk. Let's thank the speaker. Are there any questions? Either raise a hand or else just open the microphone.
Yeah.
So let me ask. So in this this equivalence between this condition on H decomposability and these S operators being differential operators, was this for any unitary reducible?
No, for square integral only.
Okay.
No.
So that is a discrete series.
Discrete series.
Discrete
exactly.
series. Okay.
Only for discrete series. We don't. I don't think there is. No. It's not known in general.
Okay.
Because the others are principal series. Sometimes for principal series, I think that there is an answer. But it's more rare to find discretely decomposability outside discrete series.
Yeah. Okay.
That's the point.
Okay.
Okay.
Are there other questions? Okay. Well, let's thank the speaker again.